Hello everyone, and welcome to this video where I'll be taking you through a problem on the objective determine table values to use for drawing trigonometric parametric curves by plotting points. So in this video, I'm going to be taking you through one sample question from a Knewton Alta assignment that is related to this particular objective, and hopefully watching me do this will help you when you go through and work on problems from that same objective yourself. As I say with most videos, most questions, when you come across a question in a video, pause it first, try to work it out on your own, and then go back, watch me work on it, and compare your work to mine, see how you're doing. Okay, so here I am at Knewton.com. And I'm in the objective graph parametric equations with the sub-objective and title of this video, the determine table values to use for drawing trigonometric parametric curves by plotting points. And there's a lot of questions I'm viewing here, but I'm just going to work on just one of them, and the rest of them in this sub-objective are pretty similar. So in this question I'm going to work on today, fill in the table of values that can be used to sketch the curve described by the parametric equations. X of t equals 3 times cosine of t, and y of t equals 2 times the sine of t, where t is in radian measure and ranges from 0 to 2 pi radians inclusive. So you see the table they got set up. You have values of the parameter called t, right? This is the independent variable for both the x and y position. The x coordinate and y coordinate depends on this t variable. And it looks like the values of t just keep increasing by pi over 6 radians, right? You got 0, pi over 6, 2 pi over 6 is pi over 3, 3 pi over 6 is pi over 2, and so on, up to 2 pi. And a lot of this table is already filled in for us. We're just asked, to find the values number 1, 2, when the value of t is 0, what's the x coordinate of your location, what's the y coordinate? Then when t is 7 pi over 6, there's space 3 you'd fill in. And when t equals 2 pi, here's space 4 that you'd fill in. Still, I'm going to go through more of it, not just those 4, and tell you what we'll be doing to actually sketch the curve. And then I'm going to go to desmos.com, a free online graphing calculator site, and we'll take a look at the curve in a better light, because my hand drawing isn't probably going to be the greatest. I'll do my best. Let's see. Okay. All right. So our two equations, the parametric equations, here are x of t is 3 times the cosine of t, and y of t equals 2 times the sine t. And I'll do the table that they were making. You have values of t in one column, then the corresponding, what's the x coordinate corresponding to that value of t, and the y coordinate corresponding to that value of t. And as I was saying, the values of t in the table given starting at 0 seem to be increasing by pi over 6, right? So you have pi over 6, 2 pi over 6, which is pi over 3, 3 pi over 6, pi over 2, 4 pi over 6, which is 2 pi over 3, 5 pi over 6, 6 pi over 6, right? So I'll start with those at least. Okay, so now for each of these values, right, this is how you plot points. And over here on the right side of the page, I'll make a little XY plane in a second. We'll plot some points for every corresponding value of t. So remember the cosine of 0, replacing t with 0, the cosine of 0 was 1, and then this is being multiplied by 3, okay? So this has an x-coordinate of 3, and the sine of 0 was 0, and then times 2, of course, is still 0, so the y-coordinate when t is 0 is 0. So on the xy plane, just making a rough sketch here, we'll go to a calculator, that Desmos calculator, in a second. Plotting the point 3 for x, 0 for y, right? So let's do this, 2, 3 for x, and 0 for y, as you're on the x-axis. And here we go, right? There's the point. I'm not going to label it because I don't want to get this too cluttered, but there's the point, 3 for x, 0 for y. And this is when, t equals 0. Maybe I'll put that there. This is when t equals 0. I know that's a little tiny, but that's when t equals 0. All right. Then when t is pi over 6, right? So now the value of t, this parameter t, is increasing. So remember the cosine of pi over 6 is the square root of 3 over 2. So this is being multiplied by 3, so that's 3 times the square root of 3 over 2. And the sine of pi over 6, for the y-coordinate here, the sine of pi over 6 was a half. And then double that, right? So 1, 2 times a half is 1. Now, the square root of 3 over 2, remember that's about 0.86. And then you're tripling this. So about 2.4, 2.5. So that's somewhere in here. And again, my handwriting is not going to be the greatest, but 3 times the square root of 3 over 2 is something between 2 and 3, maybe between 2.5 and 3. And then 1 for the y-coordinate. All right, so I got this point here. Again, we'll see a much better version on the calculator later, but there's when t equals, pi over 6. All right, so we're going from this point to that point as the value of the parameter increases. All right. Now, typically you'd throw in pi over 4 next, but it went every pi over 6. I'm just going to do the values that they have on the table for us. So for pi over 3, it's kind of the other way around, where, the cosine of pi over 3, that was a half, and the sine of pi over 3 was your square root of 3 over 2. All right, so cosine of pi over 3 is a half, times 3 is, 3 halves for the x-coordinate, or 1.5. All right, so here's 2, here's 1, here's 3 halves for the x-coordinate. And then the sine of pi over 3 was the square root of 3 over 2, and then this gets doubled, right? So that'll make just the square root of 3, which is about 1.7 something, right? So something between 1 and 2. So let's say that's here. Yeah, I'm just eyeballing things. This isn't going to be perfect. So 3 halves for the x-coordinate, square root of 3 for the y-coordinate. So around there in the xy plane, right? So this is when t equals pi over 3. All right, so we move from this point to this point to this point. So hopefully it's obvious that this is not going to be a straight line graph when I'm done. But I'll put in enough points to where hopefully we're seeing a pattern forming and fill in the rest. All right, then at pi over 2. Remember the cosine of pi over 2 was 0. So times 3 is still 0. The sine of pi over 2 is 1. Times 2 is 2. So when the value of t is pi over 2, we're at the location 0, 2. So here's 0, 2. We're on the y-axis. We're at this location when t equals pi over 2. Okay, so far it looks like we're moving in some curvy motion here, starting from here at 0, here at pi over 2. All right, and then you're going to see we're going to have pretty similar looking points with this just, negative coordinates, and you'll see. All right, so when t is 2 pi over 3, so remember the cosine of 2 pi over 3, I'm going under the x formula here. Cosine of 2 pi over 3 is a half again. So we're back to having an x coordinate. Oh, no, sorry, it was a negative half. My apologies. Cosine of 2 pi over 3 is negative half. Right? That would be a quadrant 2 angle. So negative cosine. So negative half times 3, negative 3 halves for the x coordinate, right? So let me kind of mirror this over here. So we got negative 1, negative 2, negative 3. Negative 3 halves is negative 1.5. So negative 3 halves for the x coordinate. And I'm more than likely going to see a negative 3 root 3 over 2, which is between, negative 2.5 and negative 3 over here. I'll probably see that as well. So negative 3 root 3 over 2. Sorry, these are tiny. So yeah, cosine of 2 pi over 3 is negative half times 3 is negative 3 halves. And then the sine of 2 pi over 3, that's positive, right? The sine is positive for quadrant 2 angles. That was positive square root of 3 over 2 times 2, so positive square root of 3 again for the output. All right, so at this value of t, we're at the location negative 3 halves, positive square root of 3, so over here. So here's when t equals 2 pi over 3. And then 5 pi over 6, right? The cosine of 5 pi over 6 is negative root 3 over 2, right? So there's your negative 3 times root 3 over 2 for the x coordinate of my location. The sine of 5 pi over 6 is a half, times 2 is 1. So we're at negative 3 root 3 over 2, 1. And this is when t equals, 5 pi over 6. And then when t equals pi, remember cosine of pi was negative 1, right? So we have an x coordinate of negative 3 for our location. The sine of pi is 0, and times 2 would still be 0. So we're at the point on the x-axis again, negative 3, 0, when t equals pi. So far it looks like the top half of an ellipse, right? And you're going to see that when I'm done filling this in and when we go to Desmos. This is actually going to be an elliptical graph. Now this was from 0 to pi. I'm going to do more of the table here. Let's just continue it. So I'm going from pi. It's going to kind of add to the table here. Keep going by pi over 6. Now so 7 pi over 6, 8 pi over 6, which is 4 pi over 3, 9 pi over 6, which is 3 pi over 2, 10 pi over 6, which is 5 pi over 3, then 11 pi over 6, and finally, the value of t was ranging from 0 to 2 pi, it said in the problem. 12 pi over 6 is 2 pi. And I'm hoping you can tell, based on the previous part of the table that I just covered up, right, this part here, we're just going to get the bottom half of this ellipse, pretty much points on the bottom half of an ellipse, right? When t is 7 pi over 6, cosine of that is negative root 3 over 2. So we have negative 3 root 3 over 2 again for the x coordinate. But now we have a quadrant 3 angle, right? So the sine should be negative. The sine of 7 pi over 6 was negative half, times 2 would be negative 1. So now I'm going to mirror the stuff on the positive y-axis down here, right? We got negative 1, negative 2. I'm more than likely going to see a negative root 3. So here when t is 7 pi over 6, we're at negative root 3 over 3, negative 3 root 3 over 2, negative 1. So that location. I'll keep labeling the values of t. Right? This is when t equals 7 pi over 6. And then when t equals 4 pi over 3, all right, cosine of 4 pi over 3, negative half. So times 3 would be negative 3 halves for the x-coordinate. Sine of 4 pi over 3 was negative root 3 over 2. So we have times 2 would be negative square root of 3. So negative 1.5 for the x, negative root 3 for the y. So right down there, when t equals 4 pi over 3. And then 3 pi over 2, cosine is cosine of 3 pi over 2 is 0. The sine of 3 pi over 2 is negative 1, right? So we have times 2 is negative 2. So we're at the point 0, negative 2. We're down here when t equals 3 pi over 2. And then 5 pi over 3, right? Now we're into quadrant 4 angles when you're thinking of them in standard position, right? And in quadrant 4, cosine's positive, sine's negative. Cosine of 5 pi over 3 is positive half, right? Times 3 would be positive 3 halves. And then the sine of 5 pi over 3, it'd be negative root 3 over 2. Times 2 would be negative root 3. Okay, so I'm at the 3 halves for x, negative root 3 for y. This is when t equals 5 pi over 3. And when t is 11 pi over 6, right, the cosine of 11 pi over 6, positive root 3 over 2, so times 3 would be 3 root 3 over 2. And the sine of 11 pi over 6 is negative half, right? Times 2 would be negative 1. All right, so 3 root 3 over 2, negative 1. There's that location. T equals 11 pi over 6 there. And then finally, 2 pi, we're back to the beginning of the ellipse, right? We're back to the beginning of the picture here. Cosine of 2 pi is 1, so times 3 is 3, and then the sine of 2 pi is 0, times 2 is 0. We're back at the point 3, 0. And so, when I draw the rest of them in, right, it's looking like we're doing this, right? I told you this will be an ellipse. It's a hand drawing, not great. And another thing about parametric equations, they're usually going to put also the orientation of the curve, meaning the direction the point is moving in as the value of the parameter increases, right? So you saw when t increased, we were going around the ellipse in this direction, right? Here's some little arrowheads to show me what direction we were moving in, right? So as the value of t increased, we were moving around this ellipse in a counterclockwise fashion. Great. All right, so I filled in that table. If you go back, look at the problem, right? Numbers 1 and 2 there were, 3 and 0 when the value of t was 0, x was 3, y was 0. This number 3 spot was negative 1, right? When t was negative 7 pi over 6, you had negative 3 root 3 over 2 for the x, negative 1 for the y. And the 4th spot, when t was 2 pi, you're back to 3, 0. So 4 was 3, so you got 3, 0, negative 1, 3. That would be all you'd be asked to do in the assignment. So I did way more than that was expected of me. But I just wanted to point out, what the graph would be looking like, how I'd be drawing these things. All right, so then let me show you another better picture of this curve defined by these parametric equations in Desmos. All right, so I think I've shown this before, but in Desmos, you're on the XY plane, two-dimensional XY plane here. If you want to enter parametric equations, you could be entering them as ordered pairs, right? So left parentheses, then your first equation with t, 3 cosine t, and I made sure I'm in radian mode as well. Right over here in settings, you hit the little wrench looking thing. You see radians and degrees down here. Right now I'm in radians. And then the y coordinate was, y of t was 2 times sine of t. And right, the value of t ranged from 0 to 2 pi. But you can just do 2 and then pi. And you see that ellipse that just showed up. See, this point over here is clearly, 3, 0. This is 0, 2, negative 3, 0, 0, negative 2, and then back to 3, 0. Now, if you actually want to see that motion, right, you can't really tell the orientation, right? They don't put the arrows up. Right? They don't put the arrows up. But if you'd like to see the motion of the point, I would recommend doing the following. Just type in the same stuff, but with a different letter. Because if you put in t, it's going to put in the whole thing for whatever range of t you give. T is the typical parameter. So it, does it in this standard way. If you want to see the motion of the point, do it again. So another left parenthesis, and then 3 cosine, and then replace the parameter with just some other letter. I like S. You can use any other letter, maybe just not X or Y or something, right? But just like S. So instead of T, I have S, and then 2 sine of S. And then you're going to see, instead of having a range set up, it'll ask you to add a slider for S. So I'll do that, and you can see now when S equals 1, I'll label it, I'm at this location. Now S is like T, all right? So when T is 1 radian, we're at this location where X is 1.62 and Y is about 1.68. So I'll change this little slider range here from 0 to 2 pi and have it go every pi over 6 for the step, just like in the table. And you can see when S equals 0, T equals 0, we're at 3, 0. And then there's your square root of 3 root 3 over 2 is 2.59. And then pi over 3, pi over 2, 4 pi over 3, 5 pi over 6, pi, right? And you can move around, and you can actually see, if you hit play too, it'll show you the movement. Now that jumps every pi over 6, right? It's going backwards now. If you want it to go a little more, you want to see a little more smooth motion, let's go back to this. Instead of having the step be every pi over 6 like it was in the table, I'll go every like hundredth, 0.01 or something like that, something small. And then starting S equals 0, I hit play. Maybe even slow it down. You can change the animation speed. And maybe go back to S equals 0 again. And then hit play, and you'll see the motion as the value of the parameter increases. The value, S acts like T. You see how the point is moving along this elliptical curve, in a counterclockwise direction. You can see the orientation of the curve that way. So you can play around with it, maybe change the step sizes, use other letters, whatever. But you can play around with this one. And it's pretty nice and pretty easy to see and visualize parametric curves here in Desmos. All right, and that's it. So hopefully watching this helps you out when you come across similar problems when you're trying to fill in tables with parametric equations given to you. And thank you very much for watching.